What is going on, guys? Welcome back to the Python data structures tutorial series. In this video today we're going to cover the graph data structure, so let us get right into it. Alright, so we're going to implement the graph data structure from scratch in Python today, and I think most of you guys will probably already know what a graph is. Nevertheless, I want to give you a brief theoretical explanation, just so we know what we're talking about. A graph basically consists of a bunch of nodes and a bunch of edges. So we have nodes like these here. Usually they have some label assigned to them like A, B, C, or 1, 2, 3, and so on. So let's call them 1, 2, 3, 4, 5, 6, 7, 8, 9. And these nodes can be connected by edges. So 1 and 2 might have an edge, 2 and 3 might have an edge, 3 and 4, 5 and 6, 7 and 6, maybe also 3 and 6, maybe 8 and 6, 6 and 9, 8 and 9, 5 and 8, 4 and 7, 4 and 3, 4 and 6, maybe also 1 and 5, and also 1 and 4, whatever. That would be a graph. And also, one thing that you might notice is that a tree is also a graph with a specific limitation that there are no cycles. So for example, if I have something like this, A, B, C, and then maybe D, it doesn't have to be a binary tree, it can also be something like this. This is a graph, but this is also a tree. But the moment I create a cycle like this, it's no longer a tree, but it's still a graph. And what we're seeing here is an undirected graph. So it means that the connections go both ways. 1 is connected to 2, 2 is connected to 1, and unless I specify that I want to have a directed graph, every connection goes both ways. Now, in a directed graph, every connection needs to have a direction. So 1 goes to 2, for example, but 2 doesn't go necessarily to 1. If I also want to have 2 go to 1, I need to add a second connection from 2 to 1. So that's possible, but then I need 2 connections. And every single connection has to have a direction. So we cannot have undirected and directed connections in the same graph. It's either a undirected graph or a directed graph. So that's the basic idea here. And also we can have weighted graphs. So it doesn't have to be just directed, undirected. Both can also be weighted graphs, which means that each connection has a certain weight to it. This can be a cost, this can be a speed, this can be a reward or something like this, depending on what you're trying to model. But for example, one question could be, what's the fastest road from, or the fastest path, the shortest path from 1 to 5, for example. And if this connection here doesn't have a weight, if none of the connections have weights, then of course that's the shortest path. I just have to hop once. But if I assign weights to the connections, like costs to the connections or slowdowns, I could say that this has a cost of 100. And maybe I could say this one has a cost of 50. And this one has a cost of 10. And then this one has a cost of 10 as well. Then this path already would be faster because it only costs 70 or cheaper, whatever you want to call it. But then maybe I have connections like these, 1, 1, 1, 1, 1. Then of course that's the cheapest path possible, even though I have to go through a lot of nodes. But if they're all cheap paths, I can just go like this, and that's the fastest or cheapest way to 5. So depending on whether we're working with weighted or not weighted graphs, this changes what we're looking for. Now, graphs are very versatile. They have a lot of different use cases. They're used all over the place for network analysis, for also graph neural networks, and a lot of different things can be done with graphs. But in this video today, I don't want to show you every single thing that you can do with graphs. I just want to provide a basic implementation, adding nodes, removing nodes, adding edges, removing edges. And I want to also show you some basic stuff like DFS and BFS. So BFS stands for breadth first search. We're going to talk about this in more detail when we get to the implementation. And DFS, which is depth first search. These are two things that I want to show you. Then I'm also going to provide you with the code for Dijkstra. I want to also provide you with the code for transforming or transforming the adjacency list to an adjacency matrix. And I also want to provide you with code for the shortest path algorithm, but I'm not going to explain them, so I'm just going to copy paste them. I'm going to upload them to GitHub, but these two here I'm going to actually implement with you guys in the video. I just don't want to make this video too comprehensive because we could implement a ton of things when it comes to graphs. I want to give you a basic implementation, and then you can take it from there and extend the functionality if you want to. So that's what a graph is basically. So let's get into the coding. We're going to open up a new Python file here. I'm going to call it graph.py. And this time we're only going to have the graph class. We're not going to have any node class here, even though we're going to have a bunch of nodes, but they're going to be represented as an adjacency list. Maybe that's one thing that I want to show you as well also here in the theoretical part. An adjacency list is basically how you can represent a graph. So for example, this graph could be represented the following way. I would have the adjacency list that 1 has a connection to 2, 4, and 5. And then 2 would have a connection to 1 and 3. And then 3 would have a connection to 2, 4, 5, 6, like this. That would be an adjacency list. Adjacency, come on, adjacency list. We can also have an adjacency matrix, which makes more sense or can be more interesting when we have directed graphs. But basically an adjacency matrix, the idea here is that I have all the nodes, 1, 2, 3, and so on. 1, 2, 3, and so on. And I basically say, do I have a connection from 1 to 2? If I have one, yes. Do I have one from 1 to 3? If I have none, 0. And I fill this up with ones and zeros. So that's just a different way to represent this. We're going to work with the adjacency list, and we're going to start now by saying class graph, and we're going to define the init method. We're going to pass the argument directed. By default, this is going to be false, so it's going to be an undirected graph by default. And we're going to set directed equal to directed. Also, we want to initialize an empty adjacency list. So we want to say self.adjacency list is equal to dictionary, to an empty dictionary. And then we want to define all the methods that we're going to implement. Now we're going to need a representation dunder. So repr self, this is just going to print the adjacency list. We're going to have an add node function or method where we're going to pass a node that is going to be added to the graph. We're going to have add or actually remove nodes as well. We're going to have add edge, which is going to take as parameters from node to node, and weight. By default, weight is going to be none. This is going to allow for weighted connections, which are optional. You can also have not weighted connections. We're going to have remove edge, which is going to also take from node and to nodes as parameter. Then we're going to have get neighbors for a given node. Also not too difficult to implement. We're going to have has node, which is also going to be very simple and straightforward. We're going to have also has edge from node to node. Then we're going to have get nodes. And we're going to have get edges. Now, besides that, we're going to have the two functions or methods that I talked about, which are the BFS and the DFS. So we're going to say BFS self starting from a specific node, from a start node, and also the same for the DFS. Alright, so these are the methods that we're going to implement in this video today, and I want to start right away with the representation dunder. All we're going to do here is we're going to create a graph string, and it's going to be an empty string in the beginning, and then we're going to iterate over the pairs in the adjacency list, and we're just going to display them with simple arrows. So we're going to say here for node and neighbors in adjacency list, self.adjacency list actually, we're going to just do the following. To the graph string, we're going to add the following, an f string, which is going to be the node, and an arrow pointing to all the neighbors, and then also \n, so that we have a new line, and then we're going to return that. So that's basically the graph string. Now, adding a node is also quite easy. We're going to just say if the node not in adjacency list dot keys, or actually we don't need to do dot keys, we can just do it like this. If it's not already in the adjacency list, we're going to say self.adjacency list node is going to be equal to an empty set. So we don't have any neighbors yet, we just added the node. Otherwise, we're going to raise a value arrow. We're going to say node exists already, or you can just do nothing. Depends on what you want to do. So that's that. Now, removing a node is also quite simple. If the node is not in self.adjacency list, then we're going to say raise value arrow node does not exist. So you're trying to remove something that does not exist. Otherwise, for every neighbor in self.adjacency list dot values, remove that node. So we're going to say for every set of neighbors, if this node occurs there, remove it from there because it no longer exists. So we're going to say neighbors.discard node. And then we're going to, of course, also say delete from the adjacency list this node entry. All right, so that's that. For adding an edge, we have to consider that we could have a weighted connection or we could have a not weighted connection. So we're going to say, first of all, from nodes, if the from node is not in self.adjacency list, what we want to do is we want to create it. So we want to allow for edges to be created for nodes that don't exist yet, not because this is possible, but because we're just going to add the nodes on demand. So we're going to say here, if from nodes is not in self.adjacency list, we want to say self.add nodes from nodes. This just makes it easier. We don't have to create the nodes manually and then the connections. We can just say add the connection from 1 to 2, and if both don't exist, we're going to create them. So we're going to do it like this. I'm going to copy that. We're going to do the same thing for the 2 nodes. And then we're going to say if weight is none. So if we don't have a weight, we're going to just say self.adjacency list 2 nodes is going to be, or actually from node first, from nodes 2 nodes. And then we're going to say if this is a directed graph, we want to have it only in one direction. Otherwise, so if this is not a directed, so if self-directed, or actually if not self-directed, we also want to do it the other way around. Adjacency list 2 nodes add from node. So then it goes both ways. A connection between 1 and 2 is also a connection between 2 and 1 if it's not a directed graph. And otherwise, if it is a weighted graph, we don't want to just append the node, we also want to append the weight. So we actually want to take this, copy it, paste it down here, and the only difference is that now we add a tuple, and the tuple is going to be 2 nodes weight, and it's going to be, oh, now I pressed the wrong key, it's going to be from nodes weight. And that should be it. So that's how we add an edge. And then we're going to also remove an edge. How do we do that? Well, if from node is in self adjacency list, And if toNode is in self.adjacency list from node, so if the node exists in the list and if actually the toNode is a connection, is a neighbor of from node, then we're going to just say self.adjacency list, and then from node, from here we want to remove the toNode entry, actually parentheses. So that is a case where everything exists and everything is fine. Otherwise, we want to say here, again, raise a value error. Actually, I just called this remove. It's remove edge. This will be just edge does not exist. The edge we're trying to remove does not exist. Otherwise, here we can even say node does not exist. So raise value error. Or actually, let's just say edge does not exist. It's simpler. I don't want to explain all the details of why it didn't work. But inside of here, we also want to do something else. We want to say if not self-directed, we also want to do it the other way around. So if I remove an edge, I have to remove it from both entries unless it is a directed graph. So I'm going to say here if from node in self.adjacency list toNode, if that's the case, self.adjacency list toNode remove from node. All right. So that's the removal of the edge. The other functions here now, except for BFS and DFS, are very easy to understand. Get neighbors, obviously all we have to do is we have to return self.adjacency list. Adjacency list, and then get the specific node. In the default case, just return an empty set. That's it. Get all the neighbors. Empty set by default if it doesn't exist. Has node is also quite simple. Return node in self.adjacency list. That's all we need to do for this. Has edge is also just return, or actually we need to say if from node in self.adjacency list. Then we just say return toNode in self.adjacency list from node. So is it part of it or not? This is going to return a Boolean, and otherwise we return false anyways. Get nodes is also not too difficult. Just return a list of self-adjacency list dot keys. And the edges are actually just a simple loop, or actually two loops. We're going to say edges is an empty list for from node neighbors in self.adjacency list dot items. So we iterate over the items in the adjacency list, and then we say for toNode in neighbors edges append, and then from node to node. So this is all very simple. Now I wouldn't say difficulty, but the interesting stuff happens now in BFS and DFS. So what's interesting about these two functions or these two algorithms is that we're going to use data structures that we've already talked about in this tutorial series. We're going to use a queue for the BFS and we're going to use a stack for the DFS because of the different order or the different processing order. In a queue, it's first in, first out FIFO, and in a stack, it's last in, first out. And because of that, we have these as helping data structures here. In this case, we're just going to use lists and we're going to pop the elements in different ways, but these are basically queues and stacks. So we're going to say here for the BFS, we want to have a set of visited nodes, and we want to have also a queue of nodes to be processed. We are going to start with a single node in here, and then we're going to have our resulting order, which is going to be the traversal order. And what I want to do here is I want to say, while we still have elements in the queue, we want to get the next element to be processed in the first in, first out way. So we're going to say here that the node is going to be queue.pop at index 0. to get the first element. The first element was added to the queue. And then we're going to say if this node is not already visited, so it's not already processed, we're going to go further. So we're going to say, first of all, add it to the visited nodes, and then also append it to the order, so to our resulting list. And then I want to get all the neighbors of this node. So in the beginning, all the neighbors of the starting node. So we're going to say neighbors is equal to self.adjacency list, and or actually we have a function for this, right? Get neighbors. So we're actually going to use the get neighbors function. Self.get neighbors for this node. And what we want to do now is we want to iterate over them. We're going to say for neighbor in neighbors, if is instance neighbor tuple, which means that it's a weighted connection because we have a weight. We don't just have the individual value, but we have also the weight. What we're interested in then is just the value because we don't care about the weight now. We're just going to say neighbor 0. Otherwise, we're just going to take the neighbor itself and we're going to say q dot, or actually, sorry, not otherwise. We need to do this in all cases. The only case in which we don't do that is if we have already visited that neighbor. So if neighbor is not visited, we're going to append it to the queue. So we take a look at all the neighbors that we have. Have we already processed them? Have we already visited them? If not, put them to the queue and process them further again in this first in, first out principle. And in the end, this is going to result in the BFS traversal order because we're taking in the neighbors, and since they're the first elements to be added, they're also the first elements to be processed, which is the BFS approach of going layer by layer. In the DFS, we're going to do all of that the opposite way. We're going to do that with a stack, and we're going to change queue to stack. And besides that, I think the only thing we're going to change is, of course, we're going to do pop without an index. So it's going to be the last element. And we're also going to sort the neighbors. So we're going to say for neighbor in sorted neighbors, and we're going to reverse the order. Now, I think that's not necessary, but that's usually what you do. So just reverse the order of the neighbors when you list them. But besides that, this is actually the same. The only difference is I'm going last in, first out. So whatever enters first is processed last, which is the depth first approach. This is why we use a queue and a stack. So before we go to the other functions that I have here, or actually I'm going to go through the other functions, I'm actually just going to add them here to show them to you. The reason I add them is because they have functionality that interacts with the weights, but I'm not going to implement it. I'm not going to explain it here. I'm going to provide the code to the GitHub repository, or in the GitHub repository for this tutorial series. But if you are interested, for example, in the explanation of Dijkstra, I have a video for this, or on this channel. In my algorithms and data structures tutorial series, you can take a look at the theory there. But this is the implementation here. It uses a heap, and we also have shortest path here. And also I want to use a method called toAdjacency matrix, which is going to allow us to turn our adjacency list into an adjacency matrix. So I'm going to also paste this here. Actually, this needs to be one level before. So again, these are not going to be explained. I'm just going to paste them here, and you can copy paste them from the repository. But now we want to see if our graph actually works. And for this, I'm also going to copy paste the examples here. So I already have the main section. Basically, we create a graph A, B, C, D, E, F, G. Actually, this is not even necessary because we can just create the edges. And then I'm trying to find the shortest path from A to C. Now, just so we know what we're talking about here, let's actually try to recreate this graph visually. So what does this graph look like? We have A, This is a weighted graph right now. We have A points to B, A points to C, B points to C as well. So here we have a cost of 1, here we have a cost of 10, here we have a cost of 1, then we have B going to D, D going to C as well, all with a cost of 1. We have A going to E, we have E going to F, we have G going to F. I think this is an undirected graph, so it doesn't really matter. We have F going to H, and we have H going to I, and we have I going to G, which is now this, and this one has a connection of 100, or a cost of 100, and all these have 1. So that is our graph, and we're asking the following: BFS from A, DFS from A, Dijkstra from A, and then shortest path from A to C. Let's run this. Okay, I'm calling this method EGDE and not edge, so add edge. And also I have a problem here. I need to actually iterate over the items of the adjacency list, not over the adjacency list keys. So that should be it. Let's run this. And we also have a problem. Did you mean node? This is 86 in BFS. So let's go 86 in BFS. Yeah, actually, of course, node, not nodes. Also here, node, not node R. Have some typos in here. And Q is not defined, obviously, because we're working with a stack here. So stack.append. But besides that, we also have it. We also have it here, of course. Stack, and that's it. Okay, so let's take a look at that. What do we have here? We asked for, what did we ask for? We asked for the adjacency matrix, which is what we get here. With the connection weights, we asked for the BFS from A. So we get AEC, which makes sense. So AECB, because these are the neighbors. Then we get FD, which are the neighbors of the neighbors. And then we get the rest, which is HIG. In case of DFS, we get A, B, C, D, E. So A, B, C, D. Okay, then it goes to the next neighbor, E, and then we get to F, and then it goes H, I, G. Also makes sense. Then the Dijkstra is, in order to get from A to A, we need 0 cost. In order to get from A to B, we need 1 cost. In order to get from A to C, we need a cost of 2. In order to go from A to D, we need a cost of 2, and so on. So you can just see the cost for every shortest path. And then the shortest path from A to C is A, B, C, which is of course true because A, B, C has a cost of 2 and AC would have a cost of 10. All right, so this is how you can implement the graph data structure from scratch in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.